So this is the video for Bridges, section 8.1, solving quadratic equations. Factoring and special forms. Don't be alarmed at the fact that this is in chapter 8. We actually skip chapter 6 and chapter 7 and go to chapter 8 because chapter 8 deals more with what we just got done doing. And then we'll come back to chapter 6 and chapter 7 when we're done with chapter 8. So factoring is what we've been doing, so this part should be more or less review. But let's say that I had x squared plus 5x equals 24. The thing to remember when you're trying to factor something is you have to make sure you get it equal to 0. So to do so, we can subtract 24 from both sides. We have x squared plus 5x minus 24 equals 0. When we factor that, we can either use our little factoring box, or you can realize that there's an imaginary one, not an imaginary one, an understood one. There's an understood one sitting right there. And so in reality, I just have to do an x and an x, and I have to figure out what adds to give me positive 5, but multiplies to give me negative 24. That happens to be 8 and negative 3. So if x plus 8 equals 0, that would mean that x equals negative 8. And if x minus 3 equals 0, that means that x equals 3. Now, if I had 3x squared plus 11x minus 4 equals 0. For that one, we might want to use the little factor. Whoa, that's well drawn. Little factoring box. 3x squared goes here. 11x goes there. Minus 4 goes here. Multiply going across the bottom. So now I need to figure out what adds to give me 11x, but multiplies to give me negative 12x squared. 12x and negative 1x. The greatest common factor between 12x and 3x squared would be 3x. 3x times x is 3x squared. 3x times 4 is 12x, and then minus 1 would finish it out with multiplication. So my factors would be 3x minus 1 and x plus 4 equals 0. So clearly x is negative 4, because if x plus 4 equals 0, then that would be negative 4. The next one would be x equals 1/3, because if I said 3x minus 1 equals 0, then I could add 1 to both sides, 3x equals 1, and then if I divide by 3, I get what I have up here. All right. So that's a review of how you solve these by factoring. Well, let's look at something else. Let's look at what happens when we use what's called the square root method. So, if I have something squared equals d, to solve that, I can take this and take the square root of both sides. And when you take a square root to solve a problem, you have to put a plus or minus. Because think about it, if x squared were equal to 4, x could be positive or negative 2, because positive 2 times positive 2 would be 4, and negative 2 times negative 2 would be 4. So that's why the plus or minus has to go there. And that's important. Now let's look at some examples. So, let's say I have 3x squared minus 15 equals 0. Well, unlike factoring, where you want this to be equal to 0, when you do the square root method, you want to isolate your x squared. In other words, you want to get this guy by itself. There we go. So, as a result, I can take this, I can add 15 to both sides, 3x squared equals 15. I can then divide by 3, x squared equals 5. And then, as the name suggests, I take the square root of both sides, and I get x equals plus or minus the square root of 5. And that's a perfectly good answer because 5 is not a perfect square, so that doesn't simplify at all. So notice that for this one, this part right here is squared and there's nothing else over here. So what we can do is we can just take the square root of both sides right off the bat. So I take the square root of this, I take the square root of that. When I take the square root of something squared, that square root and squared cancel, and I just get x minus 2. And then this would be plus or minus the square root of 10. Then all I have to do to get x by itself is get rid of the minus 2. I add 2 to both sides, and I get x equals 2 plus or minus the square root of 10. Or I could write plus or minus the square root of 10 plus 2 if I wanted. Both would be mathematically correct. Now, let's take a look at a couple more. 3x minus 6 quantity squared minus 8 equals 0. Well, once again, I want to try to get the thing that's squared, in other words, this thing right here, isolated. So, I can accomplish that by adding 8 to both sides. 3x minus 6 squared equals 8. Then I take the square root, and I get 3x minus 6 equals plus or minus the square root of 8. Now, unlike before, when 5 was a prime number, 8 is a perfect, or 8's not a perfect square, but it does have a perfect square that is contained in it. And so we need to talk about being able to break down square roots. Now, chances are in some math class you've seen this in some capacity, but 8 happens to be the square root of 4 times 2. So the square root of 8 is equal to the square root of 4 times the square root of 2. And notice that the square root of 4 is 2, so this is 2 square roots of 2. So this would be plus or minus 2 square roots of 2. Now, a lot of kids have a hard time remembering what their perfect squares are, so to get around that, what you can do is you can make this prime factor tree. So prime numbers are numbers that are only divisible by 1 and themselves. So like 2 is a prime number, 3 is a prime number, 5, 7, 11, 13, so on and so forth. So what I do is I look at this 8 and I say, okay, what's the smallest prime number that goes into 8? The answer to that would be 2. So 8 is 2 times 4. And then I look at 4 and I say, okay, 4 is 2 times 2. Now, what you want to do is you want to look for pairs of numbers. So yeah, on this tree you're looking for pairs, not apples or oranges. So, there's a pair of 2's right there. Now when I do this, this set of 2's acts like a single number, and that's what goes on the outside right here. So this set of 2's right here becomes this 2 right here. And then I take the leftover 2, and that becomes the 2 that's underneath the radical. Now, if there are multiple pairs that are circled, those get multiplied together, and then that would go on the outside of the radical right there. And if there are multiple numbers left over, then that would go underneath the radical like that. And keep in mind, when you're looking at this tree to simplify it, you always look at the leaves. So the stuff on the outside that doesn't have anything growing off of it, you never look at the branches. So let's finish solving this problem. So I can get x by itself. I can add 6. So I've got 3x equals 6 plus or minus 2 square roots of 2. And to finish it, I divide by 3. And I get, let's go over here, x equals 6 plus or minus 2 square roots of 2 over 3. A lot of kids will want to simplify the 6 and the 3. The problem is, because of this plus or minus here, specifically this one right here, I'd have to be able to simplify the 6, the 3, and the 2, and there's no common factor between those, so this would be your final answer right here. Now, there's only one other thing I need to discuss. Let's look at what happens when I have x squared plus 1 equals 0. Well, basically, anytime you have a quadratic or a squared term, but there's no linear term or there's no term to the first power, you can use this square root method. Okay? So I can subtract 1 to get the x squared by itself, and so that would be x squared equals negative 1. The problem is, when I go to take the square root, I would get x equals plus or minus the square root of negative 1. The problem is, there's no real number that makes the square root of negative 1. Okay? 1 times 1 is 1. Negative 1 times negative 1 is 1. There's no number multiplied by itself, the real numbers, that makes negative 1. So, as a result, we have to define a whole new number, which would be I. And I is the imaginary unit. It's an imaginary number. Okay? So, the solution to this would be plus or minus I, because we define the square root of negative 1 to be I. And so basically this would work in the following way. Let's say I had x squared plus 8 equals 0. Well, if I subtract 8 from both sides, I get x squared equals negative 8. And then when I take the square root, I end up with x equals plus or minus. Now remember, from the last screen, the square root of 8 was 2 square roots of 2. So this is 2i square roots of 2, the I coming from the fact that you've got a negative underneath that square root, and so it happens to be imaginary. Now technically speaking, you can write it like plus or minus 2 square roots of 2 times I. The problem is, if you get sloppy with this radical, then it looks like the I is underneath it, and that's something else entirely. So to combat that, we put the I in the middle, where it sits right now. Here's the last example for this section. Hopefully I can squeeze it in the next 50 seconds. Notice that there's just something squared here, so we can isolate it. Subtract 32. Divide by 2. Take the square root. (3x minus 5 equals plus or minus 4i). Add 5.